Namaste students, welcome back to online entrance exam classes. See the question. In a photoemissive cell with the incident wavelength lambda, the fastest electron has the speed v. If the incident wavelength is changed to 3 lambda by 4, the speed of the fastest emitted electron will be less than v into 3 by 4 to the power half, or greater than that, or v into 3 by 4 to the power half is equal to, or it is equal to v into 4 by 3 to the power half. Okay, how to solve this problem? See, incident wavelength is given, the initial speed is also given. Okay, the speed of the fastest electron is v for the wavelength lambda. Okay, so we have Einstein's photoelectric equation. So K maximum is equal to, so h nu or hc by lambda minus phi naught, which is the work function, right? Lambda is the wavelength of incident radiation. Okay, the speed of the fastest electron is given. For the first case it is v, so half m v maximum square is equal to hc by lambda. Lambda is the incident wavelength minus phi naught is the first case. Now in the second case, if the incident wavelength is changed to 3 lambda by 4, so then what is the speed of the fastest emitted electron? For the second case, the kinetic energy of, maximum value of kinetic energy of emitted photoelectrons is half m v dash square is equal to, so h c by 3 lambda by 4, so 3 lambda by 4 minus phi naught. So work function remains the same because it is dependent on the photosensitive material used. Okay, in a photoemissive cell, now this is a photoemissive cell, so you are not changing the emitter plate, so therefore work function is the same. Okay, so this is for the second case. Now what is asked, what is the new value of the kinetic energy, maximum value of velocity, right, speed of the fastest electron in terms of v. Okay, it is given, it is v. Okay, for the first case. So second case, for the second case let it be v dash. This is a maximum value of velocities, right, for lambda and 3 lambda by 4. Okay, so how to calculate? Okay, see, I have to express v dash in terms of v, right? See the 4 options. In terms of v, you have to express the value of v dash. If you substitute the value of phi naught here, you will not get v dash in terms of 3 by 4 or 4 by 3, right? If I substitute the value of phi naught here, okay, half m v square minus, phi naught is equal to hc by lambda minus half m v square. If you substitute here, so I am not getting 4 by 3 or 3 by 4. So the other option is, okay, substitute the value of hc by lambda here. So from the first equation we can see 4 by 3, hc by lambda is equal to, what? So half m v square minus, plus phi naught minus phi naught, right? That is hc by lambda, half m square plus phi naught. So this is equal to 4 by 3 half m v square plus 4 by 3 phi naught minus phi naught, right? So that is equal to, See, half m v dash square is equal to this much. So if I simplify, this is equal to half m v dash square, that is equal to 4 by 3 half mv square plus 4 by 3 phi naught minus phi naught. This becomes 4 phi naught minus 3 phi naught by 3, that is phi naught by 3. So what it says, half m v dash square is equal to 4 by 3, which is greater than 1, multiplied by the initial value of kinetic energy plus some constant. So what is your conclusion now? So therefore new value of kinetic energy is greater than 4 by 3 half mv square, right? Okay, so half mv dash square is greater than this value, because this value plus this value is equal to this much. Therefore this value is greater than 4 by 3 into half mv square. So half m is common, so I can conclude v dash square is greater than 4 by 3 v square. If I take the square root, I am getting the value of new value of maximum velocity, right? So that is v dash is greater than 4 by 3 to the power half into v, right? So new value of velocity, maximum value of velocity, means velocity of fastest emitted electron, is greater than 4 by 3 to the power half into initial value. Okay, so therefore option is B, which is greater than V into 4 by 3 to the power half. Okay, right. Okay, so on to the next problem, question number 11. When a radiation of wavelength lambda is incident on a metallic surface, the stopping potential is 4.8 volts. If the same surface is illuminated with the radiation of double the wavelength, then the stopping potential becomes 1.6 volts. You know, the stopping potential is dependent on the frequency or wavelength, right? Then the threshold wavelength for the surface is, what is the threshold wavelength for the surface? Okay, see, the question has two parts. When a radiation of wavelength lambda is incident on a metallic surface, the stopping potential is found to be 4.8 volts. Now for the same surface, the photosensitive material used is same, but it is the second case. When the same surface is illuminated with a radiation of double the wavelength, you are making the, you are changing the wavelength to twice the initial value, double the wavelength, then the stopping potential becomes 1.6 volts, right? Stopping potential changes because you are doubling the wavelength. Then the threshold wavelength for the surface, what is the threshold wavelength for the surface? That is lambda naught. In terms of lambda, in terms of initial wavelength lambda is incident on a metallic surface. In terms of that, you have to express lambda naught, whether lambda naught is 2 times, 4 times, 6 times or 8 times lambda. So how to solve this problem? Okay, so we have Einstein's equation, K maximum is equal to photoelectric equation, so hc by lambda, h nu or hc by lambda. So now it is given the wavelength, so therefore hc by lambda minus phi naught. Phi naught is, see what is asked, threshold wavelength, express phi naught in terms of lambda naught, which is equal to hc by lambda naught. Right? So for the first case, see, stopping potential is given, it is 4.8 volts. Right? Okay, what is the kinetic energy in terms of electron volt then? It is 4.8 electron volt. It is 4.8 electron volt, right? Okay, because the kinetic energy of the fastest electrons, which is expressed in terms of electron volt, is equal to the stopping potential in terms of volts. Numerically they are same. Okay, kinetic energy, it should be expressed in terms of electron volt, and stopping potential, which is expressed in terms of volts, they are equal. Means if the stopping potential is 4.8 volt, then the kinetic energy will be 4.8 electron volt. Okay, so this is equal to hc by lambda minus hc by lambda naught, or you can express in terms of electron volt. Okay, so 12,400 divided by lambda, which is in terms of angstrom. Okay, so hc by lambda minus hc by lambda naught. Okay, right. So for the second case, if the wavelength is changed to twice the initial value, so therefore the stopping potential is now 1.6 volt, therefore kinetic energy is 1.6 electron volt, which is equal to hc by, now wavelength is 2 lambda minus hc by lambda naught, that remains the same. Okay, work function of the metal or the photosensitive material. What is the threshold wavelength? Lambda naught is asked. We cannot substitute hc by lambda naught, the value of hc by lambda naught here. Then hc remains as it is. You have to cancel hc here. I have to cancel hc so that I can express lambda naught, threshold wavelength, in terms of lambda, right? So how to cancel hc? Divide the two equations. I mean, divide one equation by the other, 1 by 2 or 2 by 1. Okay, dividing the equation 1 by equation 2, you will get, so 4.8 divided by 1.6, that is equal to hc by lambda minus hc by lambda naught divided by hc by 2 lambda minus hc by lambda naught. So here hc is common in numerator, here in the denominator also hc is common, it is getting cancelled. So 4.8 divided by 1.6, 48 by 16, that is 3, which is equal to hc is getting cancelled, therefore 1 by lambda minus 1 by lambda naught divided by 1 by 2 lambda minus 1 by lambda naught. Right? So simplify this, you will get 3 is equal to, so lambda into lambda naught, this becomes lambda naught minus lambda divided by lambda into lambda naught, lambda naught minus lambda divided by lambda into lambda naught into, so here 2 lambda into lambda naught LCM. So this is lambda naught minus 2 lambda, right? I can write this 2 lambda into lambda naught in the denominator, so into 2 lambda into lambda naught. So lambda into lambda naught is getting cancelled, so this becomes 3 is equal to 2 lambda naught minus 2 lambda divided by, so lambda naught minus 2 lambda. Let's simplify, which implies 3 lambda naught minus 6 lambda, that is equal to 2 lambda naught minus 2 lambda. Okay, so therefore we want the value of lambda naught, Okay, so bring here 3 lambda naught minus 2 lambda naught is lambda naught, which is equal to minus 2 lambda plus 6 lambda, it is 4 lambda. So the threshold wavelength in terms of lambda, the initial wavelength is, okay, lambda naught is equal to 4 times lambda. The option is B. Okay, right. Okay, we move on to next question. Question number 12. Photoelectric work function of a metal is 1 electron volt. Light of wavelength lambda, which is equal to 3000 angstrom, falls on it. The photoelectrons come out with the velocity of, options are given, 10 meter per second, 10 to the 2 meter per second, 10 to the 4 meter per second, or 10 to the 6 meter per second. Okay, photoelectric work function of a metal is given in terms of electron volt. It is 1 electron volt. Light of wavelength lambda 3000 angstrom falls on it. The photoelectrons come out with velocity. What is the maximum value of velocity of emitted photoelectrons? That is asked. So how to calculate? We have the Einstein's photoelectric equation, K maximum is equal to, okay, light of wavelength is given, therefore hc by lambda minus phi naught. K maximum is equal to, this is 12,400 divided by, so lambda in terms of angstrom, so minus phi naught if you express the energies in terms of electron volt, right? Okay, so K maximum is half m V maximum square, that is equal to, so 12,400 divided by lambda is 3000 angstrom, so this is 3000 minus phi naught is 1 electron volt. As I told, lambda here in this particular equation, lambda is in terms of angstrom. So therefore, say this is nearly equal to half m V maximum square is equal to, so 1 2 3 0 0, nearly, instead of 4 write it as 3, so 3000 minus 1. Okay, right. So this becomes, okay, so this is 41 by 10, that is 4.1 minus 1, that is equal to 3.1, right? Okay, so this is half m V maximum square, which is nearly equal to 3 electron volt. So now we have to find out V maximum. So half into m is the mass of the electron, right? So mass of the electron is, so 9.1 into 10 to the power of minus 31, right, into V maximum square, that is equal to, so 3 electron volt, right? Okay, so into, so you have to express in terms of joules, SI unit is joules, so therefore this in terms of, if you convert it in terms of joules, therefore we have to multiply 3 by 1.6 into 10 to the power of minus 19, that is the charge of the electron, right? Okay, E. So now therefore V maximum square is equal to, so 6 into, so 1.6 into 10 to the power of minus 19 divided by 9.1 into 10 to the power of minus 31. So this is equal to 6 into 1.6 is 5 by 3, right? See, 9.1 So nearly it is 10 into, let it be 10. So this is 10 to the power of minus 19, in denominator 10 to the power of minus 31, numerator 10 to the power of plus 31. So therefore if we simplify, it is 10 to the power of 12, right? 20, 29, 31, right? So this is V maximum square. Okay, so 6 into 5, 30 is 30. So 10 to the power of 12. Therefore V maximum is equal to square root of that, 10 to the power of 6 meter per second. So option is D. Okay, so we move on to the next question. Question number 13. Two radiations containing photons of energy twice and 5 times the work function of a metal are incident successively on the metal surface. The ratio of the maximum velocities of the emitted electrons in the two cases. 1:2, 2:1, 1:4. Okay, which option is correct? Two radiations containing photons of energy twice and 5 times the work function of a metal are incident successively on the metal surface. The ratio of maximum velocities you have to find out. Okay, so we have the kinetic energy. K maximum is equal to h nu minus phi naught. So for the first case, half m V maximum square, that is equal to, see h nu is given, two radiations containing photons of energy twice and 5 times the work function. A work function is h nu naught for the first case. Okay, so that surface is incident with photons of energy twice the work function, 2h nu naught, that is equal to h nu naught. For the second case, half m V maximum square is equal to, okay, and 5 times the work function of a metal. So new value of energy of photon. So 5h nu minus h nu naught, 5h nu naught minus h nu naught, that is equal to 4h nu naught. You have to calculate the ratio of velocities. So V maximum square by V maximum dash square, that is equal to h nu naught by 4h nu naught, that is 1 by 4. Therefore V maximum by V maximum dash is equal to 1 by 2. Option is A, 1:2. See, for the same surface on a metal given, right, of a metal are incident successively on a metal, you are not changing the photosensitive material, photosensitive surface, right? So therefore work function remains the same, h nu naught. It depends on the material used. So therefore the ratio of velocities is 1:2. Okay, we move on to next question. Question number 14. Kinetic energy of photoelectrons is E when incident frequency is V1. Okay, frequency is here given as V1. It is 2E, twice the initial value, when the incident frequency is V2. What is the relationship between V1 and V2? So how do you compare? So kinetic energy of photoelectrons is E when incident frequency is V1. Okay, we have Einstein's photoelectric equation, K maximum is equal to h nu minus phi naught. See, this is important equation. In case of photoelectric effect, have only one important equation and we have different forms, right? H nu, this is EV naught or half mv square, this is h nu naught. In terms of lambda, you will have different forms. Okay, only one equation, different problems can be asked. It is 2E when incident frequency is V2, kinetic energy of photoelectrons is E. When incident frequency is V1, right? Let the work function is h V0, right? V0 is the threshold frequency. It is twice the initial value. Now the emitted photoelectrons have the energy twice the initial value of kinetic energy, that is 2E, if the frequency is V2 on that particular metallic surface. If you irradiate that particular metallic surface with the photon of energy hV2, then energy becomes twice the initial value. Okay, you have to compare these two. I mean, what about the frequencies? Okay, what about the frequencies V1 and V2? How to relate? Okay, I want V1 in terms of V2 or V2 in terms of, okay, V1, V2 I have to compare. Yeah, here V2 is in terms of V1, right? Okay, I have to compare. So just divide, cancel E here. Okay, dividing equation 1 and 2. You will get 1 by 2 is equal to, so H is getting cancelled, right? V1 minus V0 by V2 minus V0. H is common here, so getting cancelled. So therefore this is equal to V2 minus V0, that is equal to 2V1 minus 2V0, right? So that implies, so here, okay, this is minus 2V0, bring here on the left side, so you'll get, so V2, so plus V0, that is equal to 2V1, right? So V2, okay, now compare. V2 plus V0 is equal to 2 times V1. Which one is greater? Okay, if you add V0 to V2, then you will get 2 times of V1. So that implies V2 is less than 2 times V1. To get 2 times V1, you have to add V0, a positive value, to V2. Right? Okay, frequency. All are frequency, V1, V0 and V2. They are all frequencies. So therefore V2 is less than 2 times V1, because 2V1 minus V2 is equal to V0. The option is C. Okay, the next question. The cathode of a photoelectric cell is changed such that work function changes from omega 1 to omega 2, where omega 2 is greater than omega 1. So you are changing the emitter plate or cathode of a photoelectric cell such that the work function of the new cathode used is omega 2, which is greater than omega 1. If the currents before and after the change are I1 and I2, all other conditions are unchanged, then assuming H nu greater than omega naught, that is the new value of energy of photon incident on the cathode, if it is greater than the work function of the new cathode used, then which one is true? Whether both currents are equal, I1 is less than I2, I1 is less than I2, less than 2 times I1, or I1 is greater than I2. See here, you changed the emitter plate. Okay, that photoelectric cell is now having the new cathode, other cathode, right? So incident photon has the energy which is greater than the work function of the second cathode. So no doubt photoelectric emission takes place. So now what about the currents in two cases? See, current means here the saturation current. Okay, the anode voltage is kept sufficiently high. Okay, the saturation currents. What happens to the saturation currents in two cases? See, saturation currents remains same. I1 is equal to I2 because you are not changing the intensity of incident photons, right? Work function of the second cathode is omega 2, right? Incident photons have the energy h nu, it is the same. Okay, intensity is not changed. If you increase its intensity, then number of photons incident on the cathode will increase. That results in increase in current. Okay, but you are not changing the intensity, right? You are not changing the intensity. Simply you are introducing a new cathode, and the same photons, I mean the intensity of photons, they are same. Okay, so current will not change. Okay, that remains the same. Then here it is given h nu is greater than omega 2. The work function of the second cathode used, it is less than the energy of incident photons. Okay, so naturally photoelectric emission takes place. In both the cases, current will not change because you are not changing the intensity of incident photons. Okay, so therefore currents remain the same. Like I1 is equal to I2. Okay, next question. A photosensitive metallic surface has a work function h nu naught. If photons of energy 2 h nu naught fall on the surface, the electrons come out with a maximum velocity of 4 × 10⁶ meter per second. When the photon energy is increased to 5 h nu naught, the maximum velocity of photoelectrons will be. If you change the energy of incident photon, naturally kinetic energy of emitted photoelectrons change, not the current. Maximum value of kinetic energy changes and velocity changes, right? When the photon energy is increased to 5 h nu naught, 5 times the work function, the maximum velocity of photoelectrons will be. So how to solve this particular problem? A photosensitive metallic surface has work function h nu naught. Okay, we have K maximum is equal to h nu minus h nu naught. Okay, if photons have energy 2 h nu naught fall on this surface, then the maximum velocity is 4 × 10⁶ meter per second, half m into 4 × 10⁶, half m square, that is equal to h. So if photons have of energy twice the work function, so 2 h nu naught minus h nu naught, so this is equal to h nu naught, right? Half m 4 × 10⁶ whole square. For the second case, when the photon energy is increased to 5 h nu naught, 5 times the work function, then what is the new value of velocity? 5 h nu naught minus h nu naught is equal to 4 h nu naught. So divide the two, equation 1 divided by 2. So what you will get? So this is 4 × 10⁶ whole square by b square, that is equal to 1 by 4. H nu naught is getting cancelled. So you will get 4 × 10⁶, take the square root, so by b, that is equal to 1 by 2. That implies v is equal to 8 × 10⁶ meter per second. So option is C.